Hello and welcome to this presentation on utilizing vibration analysis to detect gearbox faults. My name is Jason Tranter, the founder and managing director of Mobius Institute. I hope you enjoy this presentation. In this presentation we're going to take a look at quite a number of things actually, and it is a little bit long because there are so many things to talk about, but I hope you find it useful. First, we're going to look at just the basic question of why gearboxes are more difficult to monitor with vibration analysis than other components like pumps or fans and so on. So there are some issues related to the designs of the gears and the construction of the gearbox itself, and just making sure that you get vibration readings that tell you what you want to know, but also techniques that you can use to make the vibration readings less complicated for a more complicated gearbox. Hopefully that'll become clearer as we go through. The next question we want to look at is just to understand some of the failure modes and how vibration patterns will change. Now, this isn't a detailed discussion of all the failure modes of gears and so on. It's really just looking at some of the more common fault condition and how the vibration will change. We'll look at a little bit of time waveform analysis and also how the spectra will change. And finally, how to use spectrum analysis and time waveform analysis, including techniques like circle plots and time synchronous averaging, as well as enveloping techniques to detect the faults. And because of the time constraints, we don't talk much about the enveloping techniques, but anyway, let's get on with it. So let's first look at the challenge that you are posed with when looking at gearboxes. There really are a number of challenges, and I've not listed them in any particular order, but often gearboxes are very complex but critical components in your plant. And the challenge therefore is to make sure you get it right, because the ramifications of failure can be quite severe. So, you know, you got to look at the criticality of all your equipment and make sure you're able to perform the diagnosis correctly, perform your measurements and diagnosis correctly. But certainly gearboxes can be extremely critical, and therefore it makes it even more important that you get it right. The vibration from the gearbox can be quite complicated because the gearboxes themselves can be quite complicated. Now, of course, you've got to think about the gearboxes in your plant and how complicated they are, but you can see in this case that we've got these rolling element bearings, and of course you may have sleeve or journal bearings, but you've got all these mating gears here that all generate their own sources of vibration, and you want to be able to detect if there's any problem on any one of these gears. You've got to consider the forces that will be generated, radial forces and axial forces. You've got to think about how the vibration is going to be transmitted from a mating pair of gears to the point where you are taking your vibration readings. In addition to taking the measurements correctly, we need to be in a position to detect various kinds of faults. The more severe faults, such as tooth damage, or there could be multiple teeth that are damaged. There could be anything from cracks to complete loss of metal, as in the case here. But we are also looking for increasing wear. We're looking for misalignment in the gearbox, backlash, tooth load, and one that I haven't listed up there is eccentricity, where there's some run out or actual eccentricity, or for whatever reason, maybe wear in the bearing which has moved a shaft, or but in any case, we're looking for those different sources of vibration that indicate these different types of faults, and we've got time waveform analysis and spectrum analysis at our disposal, and you want to make sure that you use both techniques. That is probably the most important message out of this. You need to do time waveform analysis, and I know I mention it later, but you should also be performing oil analysis to make sure the lubricant itself is good, and wear particle analysis to see if there are any signs of wear. Anyway, let's move along. You've also got the complication that a gearbox can have, multiple shafts that are turning at different speeds. So on the one hand, you may have a shaft that's turning at a relatively high speed, normal speed that you may be used to dealing with, but depending on the gearbox, the output speed might be a very high frequency, in which case you're dealing with limitations of transducer response and so on, because it's a very high frequency. On the other hand, you may be dealing with a very low frequency, a matter of a few RPM, and that creates its own challenges when performing vibration analysis. Now, in this presentation, that's why we run training courses. We can't cover absolutely everything. There are challenges associated with very high speeds, low speeds. There's details that we could get into regarding modulation and time synchronous averaging and these various techniques that you can use. How to detect bearing faults, which of course you'll find in the gearboxes, as well as gear faults themselves. So anyway, we'll focus mostly on the gears and mostly on just normal speed gears. Anyway, so the other thing you have to consider is just what is the design in the gearbox. Therefore, what teeth are meshing with each other, what speeds will you see, what frequencies do you expect to detect, and therefore how do you set up your spectrum measurements and your time waveform measurements in order to capture the data you need. In this case, we've got a bevel gear which creates sort of more axial vibration, and a spur gear which creates more radial vibration, and we've got certain measurement points that we can use, so we just need to be sensitive to what the forces are like, and therefore you may, in this instance, take an axial reading as well as a radial reading. But of course you've got to look at what mounting points you have available, how thick is the metal, are you going to be dealing with resonance. Some people actually use the potential of resonance to help them, because they figure, well, if the case resonates, that's going to amplify vibration. That's an interesting approach, as long as you've got good repeatability and a good transmission path from these forces through to the point where you take the measurements. But as I say, good repeatability, then you should be in good shape. As I say, gears come in different designs, and you need to make sure that you're aware of exactly what you're dealing with, and not just treat it as a generic gearbox without knowing what's going on. And of course we can have quite complicated gearboxes. In this Mobius Institute designed wind turbine, I'm just kidding, we just make animations, not wind turbines, but here you've got an epic cyclic or planetary gearbox with 2 additional stages to the gearbox. We can see it in a bit more detail here, but you can imagine that with a gearbox like this, let's say we've got an accelerometer mounted just at this location where I'm moving my mouse. You've got these gears turning at very different speeds. You've got gears that are moving in position relative to the location of my accelerometer. If you think about this gear here, it's now moving away from my accelerometer, and it's going to move back towards my accelerometer. You've got to think about the different failure modes, and that's certainly something that will help you with vibration analysis with your particular gearboxes, is to consider what the failure modes have been in the past if you've got a long history with the machine. So at least you can be absolutely making sure that you can detect those fault conditions. As everything with vibration analysis, sometimes you have to make compromises. You'd prefer not to, but in this particular instance with a planetary gearbox in a wind turbine, you may not be able to mount as many accelerometers as you might like. In a case like this, you are most likely going to be permanently mounting the accelerometers, and probably permanently monitoring the system as well. But so if you understand the design, you understand all the issues related to detecting gear faults, then you can make the appropriate choices. So a few other just quick points I'll make. Number one, you do have to understand the failure modes, as I just mentioned, but also you need an idea of the PF interval. That is basically the time between when you can detect the fault with any technique, and the time when it has functionally failed, which may be catastrophic failure, but it may be a point before there where you are basically forced to stop running that gearbox because it can no longer perform the function that it's intended to perform. So you've got a certain window of time when you can detect the fault, and of course the earlier that you detect it puts you in a position where you can decide what maintenance action you want to take, which could be anything from running the machine under lower load. It could be an option. It could be to do an inspection of the gears. It may require ordering parts, replacement gears, replacement gearbox. So everyone's situation is slightly different. So the earlier you detect it is always a good thing, but you've got to think about the PF interval, and if it happens to be short, then you need to be monitoring it much more frequently. If it's a longer failure mode, then you've got more time, but of course you've got to consider all the failure modes, and whatever is the shortest, that's going to determine how frequently you take your measurements. And as part of all of that, because you have to take all of these readings, that has a cost associated with it. We may also do wear particle analysis and oil analysis. We really should be performing those condition monitoring techniques, and that's where the asset criticality ranking is important, to understand the criticality of the gearbox, which therefore justifies what effort, what investment you make to monitor that gearbox. Of course, there's a lot more we could talk about in terms of making sure the lubricants are clean and everything, and as part of that we will perform oil analysis to not only make sure that the lubricant condition is correct, but also that it's not contaminated, which can be a very big issue in relation to gearboxes. And then we can look at wear particle analysis to see if there are any signs of wear. You may see signs of wear before you detect it in with the vibration readings. And as part of all of this is making sure the correct tests are being performed, to make sure that the samples are being taken correctly, but also that the reports are being reviewed by a competent person who can understand what those reports are telling them, so that action can be taken. So let's have a look at the gearbox vibration measurements. I mentioned this briefly before, but in a case of bearings, for example, we've got the bearing is generally at a location where you can place an accelerometer, and there are all sorts of issues, regarding monitoring of the bearings, trying to get as close as you can to the load zone, considering the design, what's the thrust versus radial components, and taking the measurements correctly. But with gears, of course, the forces that we're trying to detect inside the gearbox. So how is that vibration that will change as the gear teeth deteriorate, or if there's any eccentricity and misalignment or anything, how is that vibration going to transmit to the available measurement points? So you ideally need to know about your gearbox, the actual internal design. But whatever the case is, it's not a bad idea to start by taking measurements at multiple points and reviewing those measurements to see what sort of data you've got, and just see what you can see in that data. Make sure you can pick up the gear mesh peaks and so on that we'll talk about a little later. So let's just talk about just some of the real basics. If you're new to vibration, then this is important. With any gears, whatever the design, you've obviously got two shafts turning, typically at different speeds. So you've got to consider what those speeds are, and where they're going to show up in a time waveform, or how many cycles of rotation you'll see in the time waveform, and then also in the spectrum where those peaks are going to appear, what sort of resolution you have, and so on. And of course, in a more complicated gearbox, we'll have multiple shafts. But then, I'll just start that animation again, you've got the mesh as well. And we could talk a lot about the tooth design and so on. But ideally, in this mesh here, we don't have any backlash, which is the case where the back of the teeth are sort of making contact. That can happen for a variety of reasons, from poor design and assembly of the gearbox, even to VFDs if there's sort of shuttling of the speed, sort of fast slow fast slow fast slow, then it can cause backlash to occur, and we can detect that in the vibration analysis. But ideally what we're going to have is some sliding contact and rolling contact. In other presentations we talk about lubrication issues, but there's less than a micron between these two teeth, so the lubrication is incredibly important with gears. But from a vibration point of view, if I haven't actually counted these teeth recently, but let's say we had 31 teeth or something like that, then 31 times the speed of this rotation, we expect some variation in vibration. Now, even though that's nice, smooth, a little bit of sliding, a little bit of rolling contact, we do expect some variation in that force, and therefore a variation in the vibration at this frequency. So let's say that was 31 teeth, 31 times the speed of this shaft. Let's say this was 19 teeth. As I say, I haven't counted them, I should have done that. But it'll be 19 times the speed of this shaft. That will come out to the same frequency. It has to. That's just physics. But either way, there will be a source of vibration at the gear mesh frequency, which is the number of teeth times this speed, or the number of teeth times that speed. So we can look at this in a little more detail to see what other sources of vibration, and I will talk about other sources of vibration that we might see in addition to just these two shaft speeds and the gear mesh frequency. Now, what I'm trying to show here is here are our teeth, our gears turning, and the cycles you see in here are a simplistic view of the mesh force. So we've just got this up, down, up, down, up, down as the teeth mesh. So tooth mesh, tooth mesh, tooth mesh. Each one of these little cycles in here is a tooth mesh. That's the variation in force as the teeth come together. I'm not representing here the vibration related to the turning speed of this shaft and the turning speed of that shaft. The vibration you measure will be a combination of all these sources of vibration. What I'm focusing on here is the tooth mesh forces themselves. So that's this cycle. So as I mentioned, if there were 31 teeth here, then I'm going to get 31 of these cycles per rotation of this shaft. And if there were 19 teeth here, then it's actually 19 cycles per rotation of this shaft. So the result is, of course, one source of vibration. Now, if you look closely, you might notice that the vibration seems to rise and fall just slightly. There's some modulation. Now, when I originally recorded this webinar, there were a lot of questions about modulation, so I am going to create a separate presentation focusing on that modulation question, and you'll be sent an email on that. Or if you've just come across this in our Mobius area, then just look for that presentation shortly. But it's not uncommon to see a variation in this gear mesh force because of any run out, any eccentricity, any slight imperfection in the forces as these two gears turn. If they perfectly rotated in a circular motion, absolutely perfectly, then there's no reason for this rise and fall in vibration. So it may be slight. As we will see, that creates sidebands in our spectrum. So we expect, when we start looking at vibration analysis and we consider the spectrum, we expect there to be some vibration at the turning speed of the well, let's just say one shaft, and we've identified another peak here, which is the turning speed of the other shaft. Now I've called that 1xp pinion. By definition, the pinion is the smaller gear, and therefore that turns faster. So for the sake of this little graph here that we're going to build up over the next few slides, I've just made it a slightly higher speed than the input speed. Now it could be the output speed. The point is there are two sources of vibration. For the sake of this little demonstration here, I'm just putting those close to each other because that leaves room for all the other things I'm going to show you. So first we have those two peaks, but that's just normal vibration. Of course, there could be another one of these peaks if there's an intermediate shaft, and if there are two intermediate shafts, then we'll have another two peaks. Okay, so then we get a peak at the gear mesh frequency. So as I've described, that's the input speed times the input gear tooth count, and that's the same as the output speed times the output gear tooth count. And with a more complicated gearbox, we may have multiple gear mesh frequencies. The next question, you might have noticed these little peaks sitting around the gear mesh frequency. That is due to amplitude modulation. It can also be due to frequency modulation. Now again, I'm not going to dwell on these topics too much right now, but modulation simply means a variation, a cyclical variation in the vibration. Amplitude modulation means that that variation is in the amplitude of the vibration, and we saw that just a moment ago, and soon we'll see it in more detail. Frequency modulation is a variation in the frequency. So imagine that instead of the two gears turning at exactly the same speed from one moment to the next, imagine that there's a very slight speed up and slow down, speed up, slow down as those meshes occur. So as each tooth comes into contact, it might just slow down just that little bit, and then it speeds back up again. Then the next tooth comes into mesh, it just slows down just a little bit. We're not talking about a lot, we're just talking about a little bit of variation, and that's enough. If you visualize a sine wave for the cycles to just get a little bit closer to each other, further apart, closer, further. And that also creates these sidebands that we're seeing here. Either way, we expect to see these sorts of sidebands, but the amplitude of the sidebands and the number of sidebands and the separation, the difference in frequency of these peaks, between here and here and here, tells us about the nature of the fault condition. In addition to the gear mesh peak and the potential for those sidebands, we may see a peak at twice the gear mesh frequency and 3 times the gear mesh frequency, and in fact we may see one at 4 times and 5 times the gear mesh frequency. Now, a lot of the sort of classical vibration analysis, wall charts and things like that focus on what happens with the gear mesh, twice gear mesh and 3 times gear mesh frequency. The relative heights and how they change over time give us an indication of the different fault conditions, and you can use those rules and let them provide an indication of what's going on. I would always recommend that you also look at the time waveform. I'll talk a little bit more about that in a moment, but at the very least your Fmax, the maximum frequency displayed, which I have shown here as orders, multiples of the running speed, but whether you list it in hertz or CPM or in orders, either way it must span at least 3 times the gear mesh frequency, and you need it to be a bit higher so that there's room for these sidebands and so on. Now, when we talk about time waveform analysis, I'll try and convince you to actually make it more than 4 times the gear mesh frequency, because that'll make sure that what you see in the time waveform is more useful, and the detail you see as the teeth mesh together. Okay, now just briefly, there is another source of vibration that we can see depending on the design of your gears. Okay, so here's my Gearbox little simple simulator. Now, what I've simulated here is a situation where I do have 31 teeth here, 19 teeth here. And what I'm going to do is damage one of the teeth. You can see it moving there, and I'll just make it a bit easier to see. But what I'm simulating in this case is that this tooth, when it meshes, it's actually going to slightly damage that tooth. And then when this tooth comes into contact, it's going to slightly damage that tooth. And then when this tooth comes back into mesh, it'll slightly damage that tooth. And then that damages that. And this will damage, or they're going to mate with each other. And this will touch there. And if we keep watching, we'll see an interesting thing happen. That from now on, notice that there are a few points on this gear that are red, and a few points... Oh, no, sorry, no, I'm getting ahead of myself. If we keep watching, we'll see that eventually every single tooth will go red. So I'm getting ahead of myself for the next point I wanted to make. Okay, so if we speed up the animation just so that we're not waiting too long, you can see now that all the teeth are red. Now that means that if any tooth is slightly damaged for any reason, it may be that the lubricant is contaminated. It shouldn't be, but let's say it is, and some hard particle goes through and slightly damages the tooth, and that makes that tooth imperfect, and then that mates with the tooth, you know, on the mating gear, and that has the potential for slightly damaging that tooth. And as you can imagine, these gears are just turning, and so this is just repeating. Same could be true if when the gearbox was transported or installed or whatever, you know, two mating teeth may just damage each other, and as the gearbox rotates, that damage, that imperfection, has the potential to spread around all the gears. Now, in this design, which is how gearboxes are supposed to be designed, the number of teeth are prime numbers. So we've got 31 teeth. Now, 31 is divisible by 31. It's divisible by 1, but no other number. You know, you can go through them, 1, 2, or 2, 3, 4, 5, 6, 7. Anytime you try and divide 31 by 2 or 3 or 4 or 5 or 6, etc., all the way up to 31 itself, if you divide it through, you won't end up with a whole number. And it's the same with 19. 19 is divisible by 19 and 1, but by no other number. So that makes them prime numbers. And gearboxes ideally will be designed with a prime number of teeth. And this is the reason. The wear spreads more slowly. The wear is spread evenly across all of the teeth. And therefore, as this wear spreads very slowly, as a normal process, the fact that all of the teeth are sharing in that process, it means the gearbox has a longer life. Now let's look at a different situation. Now we're going to do something else. We've got actually 30 teeth on here and 18 teeth. Now what I'm going to do is fix the teeth, only that easy, and we'll damage one tooth, and we'll just speed up the animation a little bit. So it damaged that one just a little bit, that damaged that one, that damaged that one, that damaged that one, etc., etc. Now if we keep watching, in this instance we will see the strange thing that I started to mention before, and that is, no matter how long we wait, no additional teeth will come into contact with those red teeth. So let's say the gearbox was being transported, 2 teeth were damaged, those teeth now potentially wear against other teeth, but now only 5 teeth on this gear and 3 teeth on this gear are taking that extra wear, and that means that those teeth will wear far more quickly than would be the situation if there was a prime number of teeth. Now we can get into all these calculations. You see, we have these non-prime numbers. See, 30 is divisible by 1, it's divisible by 2, 30 divided by 2 is 15. 15 is divisible by 3. 15 divided by 3 is 5. And that leaves 5 as the sort of remainder. And we can look at 18 divisible by 1, by 2, by 3. And then that final result is divisible by 3. So we have these common factors of 1, which is always a common factor, 2 and 3. And we multiply them together and we get 6. So I'm rushing through this part, you know, otherwise this webinar would go for hours. But the key thing is here that if you look at this one and you go through this calculation of the prime factors, notice that the largest common factor, prime factor is 5. 1, 2, 3, 4, 5. There are 5 teeth on this gear that are going to take the wear in this instance. In this one, the highest prime factor is 3. We've got 1, 2, 3. So you can imagine that 3 times the speed of this gear is potentially going to create a source of vibration. So if we actually simulate that, then we expect to see these peaks show up. The gear assembly phase frequency is what it's called. Gear assembly phase frequency. So if you like, it's 3 times one frequency, so it's 3 times this one, or 5 times this one. It's the same frequency, 5 times this, 3 times that. Remember, this is turning faster, so 3 times that is equal to 5 times that. And so we may see a peak. You might see a peak in your spectrum and say, what is that? It happens to be a 1/6 of the gear mesh frequency. So there's my product of my common factors. They are the prime factors that are common to both gears. And so our gear mesh frequency divided by 6 is this. And we got harmonics of it. Of course, there's 6 harmonics. 1, 2, 3, 4, 5, 6. Anyway, all the math work out. The point is you can see these peaks. Now, as I said, ideally a gearbox will be designed with a prime number of teeth. But if there's a specific design that was required, there may not be a combination possible with prime numbers. So they have to use these non-prime numbers of teeth, and therefore this is a source of vibration that you may see. What I'll also mention just while this is going around is that when you have any source of vibration, there is potential to excite resonances. And if you imagine taking this gear out of the gearbox, suspending it on some sort of cord and hitting it with a hammer, it's going to ring. It is a metal object. Now, when it's in the gearbox, even though it's mating with the other gears, it's on a shaft which is supported by bearings and so on, it still has a natural frequency. It may be different because the stiffness is changed and so on because of the configuration, but it still has a natural frequency, and therefore we have the potential to see additional peaks in the spectrum related to that natural frequency. And if we have any fault conditions which can excite that natural frequency, any impacting sort of faults with damaged teeth, then that natural frequency will be excited with a higher level of force, if you like, and therefore that peak can rise. We can also see modulation in that vibration. Instead of it being a solid impact, if that force of that impact rises and falls, then our gear natural frequency may also have sidebands. Anyway, this just explains why sometimes you might look at gearbox vibration and see peaks that you can't quite explain. They could be related to natural frequencies. They could be related to this gear assembly phase frequency. Okay, so moving right along. Here is an example, actually, of a photo of a damaged gear, but you notice that it's damage, 1, 2, 3, 4, perfectly good teeth, damage, 1, 2, 3, 4, let's go in the other direction, 1, 2, 3, 4, damage, 1, 2, 3, 4, damage, 1, 2, 3, 4, damage. Chances are, if we could count the number of teeth here and look at the mating gear, then we would see these same common factors. Now this is a rather severe example, but hey, you can see what I'm talking about there. Now there's one more source of vibration that sometimes comes up. Is called the hunting tooth frequency. Now it's related to this very same issue. However, what I'm going to do here is damage one tooth, and what we're going to look at is how frequently does this tooth come into contact with that tooth. So we're not talking about how the wear spreads. We're just interested in how often a individual tooth on one gear comes into contact with an individual tooth on the other gear. If we keep watching, they finally came into contact with each other. And if we wait for a while, they'll finally come back into contact with each other. So anything that doesn't happen frequently is going to be a low frequency. So from a spectrum point of view, if I put in my hunting tooth frequency, it could be quite a high peak at quite a low frequency. That's just because those two individual teeth don't come into mesh very frequently. So again, if we go back to that possibility that when the gearbox was transported, two teeth were mating at the time and they were damaged, then you can get a particular source of vibration every time those two teeth come back into mesh. That's going to be the sort of the worst vibration just when those two teeth come into mesh. When those two teeth mesh with other teeth, there's going to be a heightened amount of vibration because the teeth aren't perfect. But when those teeth come into contact with each other, then the vibration is even worse. And so you may hear this low frequency kind of growling sound coming from the gearbox, and this could be the source of that vibration. There are possibly other reasons why those two teeth were damaged, but either way, this is the nature of the vibration. And there's a complicated calculation you can go through which involves all these prime numbers and all this sort of jazz to determine. But basically, we can have a peak in the spectrum, and it could be quite a high amplitude peak, and we'll see it in the time waveform as well if we've set it up properly. Okay, let's have a look at some simplified spectra. Now, here we're talking about just tooth wear. So the two teeth have become damaged. I should say all the teeth are potentially worn to some degree, and we will see an increase in the vibration. So you've got to imagine that these teeth are just, instead of being a nice smooth contact in the gear mesh, they are now rough, if I can just put it that way, and therefore that vibration will change. Now, I've pointed out a couple of things in this sort of classic type of spectrum. Here's our gear natural frequency peak. It could show up anywhere, it's whatever the natural frequency is. And because of the nature of the vibration, we might see some sidebands around that. That's one thing. But we're also just looking at how this gear mesh peak changes in amplitude. If the teeth are wearing, there's no real reason for a change in the sort of cyclical force of the gear mesh. The force between each gear mesh doesn't necessarily change from one point on the gear to another point as the gears turn. Therefore, modulation isn't the real big issue in this case. Remember, modulation occurs when the vibration, the force in that gear mesh changes per rotation. But if the teeth are all wearing basically evenly, then we have a heightened amount of vibration at the gear mesh frequency. Now, here's where I'm showing, gear mesh, twice gear mesh, 3 times gear mesh. You may see 3 times gear mesh rise in amplitude. Look, these are guides. They've sort of been published. The vibration's been experienced. But particularly with gearboxes that are potentially quite critical components, I would be reluctant to make a call purely on what I saw in the spectrum. Number one, I'd want to look at the time waveform. Number two, particularly in a case like this, I'd want to look at the lubricant itself, because if there is wear, that means there will be metal particles of the metal that is used to make the gears. I expect to see that in the lubricant, and a experienced analyst or lubrication analyst, wear particle analyst, can look at the shape and size and color of those particles and tell you, yes, wear is occurring. So yes, vibration may be an indicator. Ideally, you would have already been doing oil analysis, and you should be getting warnings from that technique as well. But every additional piece of supporting information you can get is always helpful when you're making a call like this. So obviously with tooth wear, there should be clear signs in the lubricant. The root cause may be also present in the lubricant as well. Maybe the viscosity is incorrect. Maybe the wrong lubricant has been put in there. Perhaps the lubricant is contaminated with water or with particles that's causing that wear to occur. Tooth load is a different situation, where the forces in the mesh itself are higher. So you can look at the possible reasons for that to occur, but we're just driving that gearbox harder. The force as each tooth comes into mesh is higher, and therefore we expect the gear mesh peak to go up. It's just a normal source of vibration. It goes up. Again, we can look at that and say, well, yes, if there was any eccentricity, then that's, the effects of that eccentricity would be heightened. But because we're focusing on tooth load, the real indicator is just that the amounts of vibration in this gear mesh peak will go up. Now, we might always expect to see twice gear mesh and 3 times gear mesh. Because they're harmonics, anytime you've got non-linear vibration, it's just not smooth vibration, we expect to see those peaks go up. But the real telltale sign with tooth load is the gear mesh peak rising up. Now, in the instance of gear eccentricity, the situation I'm trying to depict here is where, if you look very closely at this gear, it's turning correctly around the axis of rotation of this shaft. So the shaft itself is not moving, the gear itself as it turns is moving in a perfectly circular motion. But when we look at this one, in actual fact, if you look closely, the way I've animated this particular situation, the shaft itself is moving in a circular orbit. So if I leave my mouse in one sort of reference position, you can see that the shaft itself is moving in a circular motion. That means that the force in the mesh here will increase in force, then decrease in force, increase in force, decrease in force. Now, this could be because of a bent shaft, for example. We may have a situation where the shaft is turning correctly on its axis, but there is eccentricity in the gear itself. Maybe because of manufacturing, maybe because of the way it's been installed. You have to sort of consider the possibilities for why this is occurring. But any time we have this variation in the gear mesh force, we see more of that modulation. In this animation that we see here, we've got the 2 gears meshing together eccentrically. So, it's, as I've already said, it could be because of a bent shaft, it could be because of the gear manufacturer or whatever. But if you look closely, we see the forces are much higher now, and therefore we get a higher amplitude of vibration. When the gears are further apart, we get a lower amplitude of vibration. So you can see there's more force in the mesh, less force in the mesh. More force in the mesh, less force in the mesh. Now, with my animations and everything, I'm exaggerating things and I'm simplifying things. So on the exaggeration part, I'm showing this mesh. So it's a tooth meshing, a tooth mesh, a tooth mesh. So that's what this cycle is here, as I described earlier. And then in my animation, I'm exaggerating the amount of movement. I mean, if I didn't exaggerate it, you wouldn't see it. But what I'm trying to illustrate here is that if for any reason one of the gears is moving in this sort of circular motion, then we will see the same gear mesh frequency. There is still the same number of teeth on the gear, so we see that same gear mesh frequency, but the amplitude, the force in the gear mesh, rises and falls per rotation of the eccentric gear. So in this case, we're seeing this rotate around. Well, that's the from the top here to the top there is one rotation of this eccentric gear. So it rises up when the force is greater, falls down when it's weaker, rises up when it's greater. And when we see this sort of vibration, we can see that in the time waveform. It won't be as clean and pretty as what we're seeing there, but you will see it in the time waveform. But you will see it in the spectrum as well. So if we have a look at this, what we're seeing here is, yes, our good old gear mesh peak and some vibration at twice and 3 times gear mesh. But the real telltale is that our sideband amplitude has risen up. We get all these sidebands in part because of amplitude modulation that I've explained, in part because of frequency modulation, that as those gears come into, as each tooth comes into mesh, we get a slight speed up, slow down, speed up, slow down. The result is that you are looking for these sidebands. We may also see the gear natural frequency being excited. It may also have sidebands around it, but the real focus we're looking for here is that the gear mesh peak itself may not rise up a lot. It will rise because there is overall greater force in the mesh, so we may see that go up, but we're really looking for the sidebands increasing in amplitude. And because it's non-linear vibration, we always see multiples of a source of vibration, so multiples of our gear mesh frequency, because it's not nice, simple, smooth vibration. In the case of misalignment, we've got one gear which is not aligned correctly to the other gear. It could be an assembly error, it could be that there's excessive wear in one of the bearings. There's various possible reasons, but if you look at this exaggerated animation, we're not really expecting there to be a lot of modulation in that vibration. The two gears are sort of at a fixed relative position, assuming that that is the case, and therefore our gear mesh force will have changed because of the misalignment, but it's sort of constant per rotation. So in this case, we may still see sidebands as normal, but we see a change in the vibration. And just as we often do in relation to normal misalignment between motors and pumps and so on, we may see that twice gear mesh frequency will increase in amplitude more than just the normal gear mesh peak. But the bottom line is, I guess with all vibration analysis, one of the things that I think is the most important ability of a good vibration analyst is to be able to transform yourself down and think about what's happening inside the machine. You can do it in one of two ways. You can think about the various faults and think how that's going to change the vibration. What forces will change? What modulation will occur? Is there impacting, how is the vibration changing? And that way you can imagine why the spectrum changes the way it does. But on the other hand, you have to be able to reverse that process. You need to look at the vibration and say, why is it so? Why am I seeing these changes? Why is the modulation changing? Why is the gear mesh changing? And go backwards. That's the truth in the case of analyzing gearboxes, but it's the truth no matter what you're doing with vibration. Bearings, pumps, whatever the vibration is. It's really helpful to be able to relate what you're seeing in the vibration to the machine, because then you don't have to remember wall charts and so on. You don't have to sort of just take guesses because, well, it sort of looks like that. I mean, this is a big call you're making. Do I stop this gearbox? Do I have to order parts? And they could take a long time to be delivered. It could be very expensive. It's really important that you get it right. But obviously it's also important to take your measurements so that you can see those peaks up to 3 times gear mesh frequency, and as I'll mention soon, I would go up to 4 times, but also so that you have enough resolution to see these sidebands. So let's talk about time waveform analysis. I've mentioned it a lot of times. It is a very, very important tool in relation to gear analysis. The time waveform is the truth in vibration. As long as it's measured correctly, it is really telling you what is happening inside your machine from one moment to the next. So as the teeth mesh together, as the rolling elements roll around, if there's a damaged tooth, if the teeth are worn, if the forces are rising and falling, whatever the situation is, the time waveform is telling you exactly what happened from one moment to the next. And then we do an FFT, and that just looks at all of the time, all of the vibration, and says, hey, I'll give you a summary of what happened. So in this instance, we're seeing something very, very important in this time waveform, and I'll elaborate on it shortly. But in here, this low amplitude vibration is the vibration we expect to see as the teeth, as good, healthy teeth mesh together. but the spikes relate to a damaged tooth coming through the mesh. So the damaged tooth comes through, healthy teeth. Damaged tooth, healthy teeth. Damaged tooth, healthy teeth, etc., etc., etc. Our time waveform tells us exactly what's going on. We can see that there are spikes. If we know, if either we set our x-axis up in rotations of the shaft, we would see that for the gear with the damaged teeth, this is 1 rotation, 2 rotations, 3 rotations, 4 rotations, and so on. In this particular instance, the time waveform has been beautifully set up so that I can see enough of these events. And I'll talk more about this in a moment, but there are 2 keys with time waveform analysis. We want to see the events occurring. We don't want to miss the events, but we don't want to have so many of the events in our time record that they kind of get smooshed together and we can't see them. So here, you know, for the speed of this particular gearbox, we needed just over 3 seconds of time to capture 1, 2, 3, 4, I won't count them all out, but you can see there's a limited number of teeth coming into mesh so that I can easily see what's going on. That's perfect. And I'm also sampling fast enough so that I can see these events. If I wasn't sampling fast enough, I could miss them or not get a detailed picture, and I'd certainly get the amplitude wrong, but I'll elaborate on that in just a second. So time waveform analysis is important. One of the reasons it's important, one of the reasons why it is important is because the FFT process has limitations. The FFT is looking at this whole time record here and trying to come up with one set of peaks in a spectrum that represents all of that. In some cases it does a great job, you know, with normal unbalance and simple sources of vibration. It does a good job, and we can see harmonics and sidebands in the spectra and try to interpret what that actually means in terms of the machine, and therefore what is really happening in the time waveform. But hey, the time waveform's telling you. But when we get even more complicated time waveforms, or therefore vibration from the machine, the FFT becomes even more limited. What you've got to imagine inside the machine is we have this vibration just coming from the machine, whatever it looks like, and the analyzer grabs a chunk. The time of this chunk, or this time record, is based on the lines of resolution setting. So it grabs that, it windows it, calculates an FFT, and grabs another chunk, and there may be overlap, and it windows that and calculates another FFT, and does it again and does it again, and we end up with these 4 time waveforms, and 4 spectra, and we average it together. So with normal vibration, this is just fine. There are limitations, and I've talked about those limitations in other webinars and certainly in our training and so on. But the fact is that for normal processes, that's an acceptable process. But when you got more complicated vibration from a gearbox, all this windowing and averaging and all of that can really sort of lose the information that we ultimately want to see. When you do time waveform analysis, we are keeping one of these time waveforms and analyzing it. Or we may take a separate time waveform measurement which is ideally suited. You know, we might take one measurement which is ideally suited for the spectrum and another one which is ideally suited for the time waveform. I'll elaborate on that in a second. But the fact is that, you know, when we take those 4 spectra, you know, we average them together. We say, you know, depending on the technique we use, we end up with just this average, and that's fine for normal vibration analysis. But for time waveform analysis, for gearbox analysis, I think it's too limited. You need the time waveform. Coming back to this time waveform we were looking at before, this was the situation. So every time this damaged, or these 2 damaged teeth came through the mesh, we got this spike of vibration. All these other healthy, well lubricated for now, or well, healthy for now, it just depends on what happened to the chunks of metal and so on. But the bad teeth come through, we get the spike. The good teeth, the bad teeth, the good teeth, the bad teeth. This tells us exactly what's going on. I know which gear is damaged. I get a sense for how badly it's damaged. You can look at these G levels and then get an indication of the severity, but you've got to remember there's transmission path issues. How is the gear vibration attenuated and so on. The time waveform is telling you exactly what's going on. Just a quick primer on the time waveform. I'm taking way too long on this presentation, but I hope you're finding it useful. Imagine that what we're seeing going past here, I'll slow it down. What we're seeing here is the real vibration. Imagine if I could sample it 1 billion times a second so that we knew exactly what was happening from one split second to the next. Let's just assume that that is the real vibration on the machine where we've placed the vibration sensor. Now what I'm going to do is I'm going to come along with this analyzer, and what it has the ability of doing is at certain time intervals it's going to say, what is the voltage now from my accelerometer? The accelerometer is sensing that vibration on the gearbox. And there are issues we could talk about with the mounting resonances and the response time of the accelerometer and all sorts of things. So the analyzer says, I'm going to take a voltage reading now, etc. You can see them. But if those time waveform, if the sample time, the time between each one of these samples is too slow, you can see that the waveform, this green trace here, is what the analyzer will remember and then put through the FFT and display to you in a time waveform window. Well, this green trace has nothing to do with the real vibration, does it? It's obviously poor. We are obviously sampling too slowly. So we speed up the sample rate, the number of samples per second. From our FFT parameter, you will either have the option to change the number of samples per second, or you'll have the option to change the Fmax. This has nothing to do with the lines of resolution setting at all. It's all to do with your Fmax setting, or you may have direct control. So what I'm going to do is I'm going to increase the sample rate faster and faster. And ideally we'll get to a point where we're sampling it fast enough that our green trace looks, well, ideally identical to the original real blue vibration. But this is what you have to select with your measurement settings. You have to say, how fast is fast enough so that I can see exactly what's happening as these teeth come into mesh. Because if I've got one damaged tooth, then as that tooth comes into mesh and the forces all change and therefore the accelerometer is experiencing that, I want to get lots of these digital values, these voltage readings from the sensor as that tooth comes into mesh. I might like 10 little voltage readings as that tooth comes into mesh, so that A, I can see it clearly in my time waveform, and B, more importantly, as that vibration changes, we want to capture it. If we've got any really sharp spikes, we could take a voltage reading on either side of the spike and never see the true vibration. I can't illustrate that easily, but if you look here, you'll see just here that there's a blue spike that goes up, but we didn't capture that. The green captured waveform is lower. We ideally wanted to get a digital sample up top here. You can see it there as well. We didn't capture these spikes. We sampled, even now we're sampling too slowly. We might just fluke it. You can see here we fluked it and captured the peak of the time waveform, of the true vibration, but here we didn't. I hope you can see the difference between the green and the blue. Here we didn't. See that spike? Well, you could be having 20 G spikes but never know it because you're sampling at too low a rate. Here's a perfect example. Look at this great big spike here, but our captured waveform looks nothing like it. So we need to sample very, very quickly. And as a rule of thumb, I wouldn't want to have anything less than 10 samples per event that I was interested in this case tooth mesh. I'll explain how you can set it up correctly in just a second. Anyway, that's the time waveform process. So I want to sample fast enough to capture all the lovely detail that I'm interested in. But when I look at my time waveform, I don't want to have so many of those events that they all get smooshed together like I mentioned before. I would like to have 6 or 10 or maybe 15 on my time waveform plot so that I can see that these things are actually happening. And then I can zoom in and look at them a bit more closely if I want to, but at least I can see them. If the time waveform is not long enough, I may not see the events at all. There are situations, I mentioned the hunting tooth frequency before, you might listen, as in with your ear, to a gearbox and hear click, 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 as two particular teeth come into mesh with each other. Your time waveform could start and end between those little clicks in the gearbox. Or you might, in the time of your time waveform, have lots and lots and lots and lots of teeth meshing together, and therefore that variation in vibration is just not seen because there's too many events per cycle. Now, let's consider another way of collecting our data. In a normal analyzer setting, when you walk out to the machine, even if your analyzer is set up correctly, and you press the start measurement button, it will just start collecting the data, just sort of like I described before. So here's the vibration, whatever it is, and these little marks indicate revolutions of the shaft, and down here I've got my tack signal just for now as a reference. So let's just zoom in on that. So there's just 2 revolutions of the shaft, and the vibration I'm seeing here in my little simulation is I've got 1x vibration, 5x vibration, 7.2x vibration. Now that might be, bearing frequency, for example, and I've got noise on top of that. So that's what's in this waveform up here. Now, when the analyzer normally works, what it does is it grabs a chunk. It might be 1024, 2048, 4096. It just depends on your number of lines of resolution. It's going to grab a chunk, take that out, and do the windowing and calculate the spectrum. It's then going to grab another chunk. Now, what I'm illustrating here is no overlap, but the point is the analyzer, as soon as it just keeps on sampling, it just keeps on taking chunks of the time waveform, and if I was to look at each of the time waveforms in this little time record, in this time record, in this time record, let's just call it average 1, average 2, average 3, average 4. Well, if I look at them sort of stacked above each other, you can see that there's no sort of commonality between them. In other words, this one goes high at the same time as this one's sort of at the midpoint in its cycle. This one's going high here, where this one's at the sort of the midpoint, and so on. Anyway, the point is that if I was to use my analyzer to average the time waveforms, not the spectra, but the time waveforms, you can see that would be a pointless exercise because these things are just going to average each other away. That's the normal function of an analyzer. But we can use something called time synchronous averaging. And the difference is that the analyzer will, when you press the go button, it'll say, okay, I'm going to start digitizing internally, but I'm not going to save the data until I see a tack pulse come along from the shaft of interest. So the tack comes and says, oh good, let's go. And it grabs our 2048 time samples. And when it finishes, and during that time there'll be a certain number of revolutions of the shaft, it'll finish, but rather than capturing this data as well, it says, wait, bang, there's another pulse that's come from my tack signal. Start saving these samples again, and it'll go again. So what we've done is we've synchronized our sampling to the rotation of the shaft. We've just waited this little bit and started sampling at the same point in the cycle or the rotation of the shaft. So we do it once, we do it again, we do it again, we do it again. So this is this one expanded, etc. for that one, and this one for that one. Now if we look at these and we overlay them on each other, you can see that the dominant sort of once per revolution vibration has now been synchronized. Those waveforms overlay on each other. But what happens is if you average those, well, in this case we've just got 3, but let's assume we did it 100 times. It takes quite a few of these averages to weed out the data. What happens is anything that's not synchronous with our once per revolution, tack signal, gets averaged away. So our bearing frequencies get averaged away, the noise gets averaged away, and the gears that are turning at a different rate also get averaged away. So that the gears that are turning at the rate where this tack signal came from will remain. Any vibration synchronous with that will remain. Everything else will be removed. And so if we were to look at what is inside this, well, we've got the 1x plus 5x, because 1x and 5x are synchronous and integer multiples of 1x. So you can see that the time synchronous average data is exactly the same as just the 1x plus 5x data, but this shows the 1x plus 5x plus 7.2x. The 7.2x has been averaged away. Anyway, we don't really have time to keep yakking about this, but I hope that sort of clarifies why you'd want to use time synchronous averaging. Now, one of the big questions that often comes up is, well, how do I do it? Ideally, you would stop the machine, you'd put a bit of reflective tape on the input shaft, you would set up your analyzer and say, okay, I want time synchronous averaging, but my trigger signal's coming in from that input shaft. And you would take the measurement, you need lots and lots of averages, and you will end up with a nice clean time waveform. You can analyze that time waveform, and we might use a circle plot, which I'll describe in just a second, but we can look at it just on a normal plot as well. But if it's just a simple single stage gearbox, then that's fine. However, if you've got multi-stage gearbox, well, you just averaged away a lot of gear vibration that you are interested in. So now, ideally, you would also get a tack signal off the intermediate shaft, or in every shaft that's in the gearbox. Now, you may not be able to do that, but thanks to the wonders of software and electronics and so on, there is an easier way. You still need a once per rev sort of reference signal that comes from the gearbox. You still need something that tells you, at least for one of the shafts, that you need this one tack signal. But you can either use a tracking ratio synthesizer, or your analyzer may have the internal smarts to do it. And what it basically does is it says, okay, this is the once per rev of the input shaft, and I know that the intermediate shaft speed is at 4.67 times that speed, or it might be, at a lower speed. Whatever it is, you tell the tracking ratio synthesizer or the analyzer what that ratio is. And if you like, it synthesizes the tack signal that would have come from that intermediate or output shaft. Okay, so it's creating the tack signal that you are unable to measure. So again, you will have multiple measurements for each shaft. However, you only need the one tack signal. The analyzer will do one measurement, then you set it up and say, okay, well, the ratio between these two shafts in the gearbox is whatever it is, speed increase or a speed decrease, and it'll give you a good time synchronous averaged time waveform, which again you can look at as a spectrum, but you sure want to look at it as a time waveform as well, because any damage to any teeth will show up very, very clearly. So, as I mentioned before, we would ideally capture a minimum of 10 samples per tooth mesh. Now you can do all kinds of calculations in terms of what's the speed of the machine, what time does it take for a shaft to rotate, how many teeth are there, therefore what proportion of time are the teeth in mesh, and so on. There's another simpler way to do it. It takes a bit of an understanding of how the analyzer works. The fact is that when you choose an F max for your analyzer, the analyzer itself is going to retain for you a time waveform that is sampled at 2.56 times the Fmax. So let's say we had a 1000 Hertz Fmax, and therefore the analyzer is going to sample at 2560 samples per second. Now, that means that if there was a peak in the spectrum right at the right-hand end of the spectrum, so this is the time waveform, I apologize. Imagine this is a spectrum, and we've got a peak right up here. And let's say that peak is the gear mesh frequency. So that relates to the the gears meshing together. Well, if the peak was right here at the very end of my spectrum, that means that as the teeth mesh together, I'm getting 2.56 samples per tooth mesh. You can sort of do all the maths if you like, but that has to be the way it works out. So then if I increase my Fmax, I'm increasing the samples per second, which means I'm increasing the number of samples per tooth mesh. As these tooth come into mesh, I get more samples. Well, if I doubled my Fmax, now that gear mesh peak will be in the middle of the spectrum, and therefore I'm going to get 2 times 2.56 samples per mesh. In other words, it'll be 5.12. Well, what if I put my gear mesh peak a quarter of the way along my spectrum? So therefore, the number of samples per gear mesh will be 4 times. If it's at a quarter, then it's 4 times 2.56, which is approximately 10 samples per tooth mesh. So the simple thing is, if you set up a spectrum that is a minimum of 4 times the gear mesh frequency, you will have at least 10 samples per tooth mesh. That should mean that the spectrum you get is good, because it's you'll see 4 times gear mesh in your spectrum. That's good, and the time waveform should be good. Now the other part of it though is that the resolution dictates how many samples you see. As you increase the resolution, the analyzer keeps on sampling at that same rate. It just samples for a longer time and uses that for your FFT. Now for the spectrum, you do want nice high resolution because you want to see all those sidebands, but for the time waveform you only want to see 6, 10, 15 of those tooth mesh of those rotations of the shaft in the time waveform. Anyway, so that hopefully gives you an idea of how to set it up so that you get a good time waveform. Okay, now we can analyze the time waveform in a normal sense with the x-axis as time in seconds or milliseconds. A lot of software will let you change that to be revolutions, so we can sort of see what's happening per revolution of the shaft. And that's sort of what I'm seeing up here. So this is just some vibration. I'm getting 1, 2, 3, 4 cycles per revolution, or 4 events per revolution. So I can look at that as a time waveform and say, yep, that tells me what's going on. But remember, when we look at a time waveform, what we're interested in here is what's happening as the shaft turns. The shaft is round, so wouldn't it be cool to display that time waveform in a circular format so that we can really relate what happens as the shaft turns? Well, that's what a circle plot does. So if I just expand and say what happened per revolution, 1, 2, 3, 4, right, just as I said, let's wrap that around a circle. So we wrap it around. What we're doing is we're saying, this is 1 revolution of the shaft. So as the shaft turns, this is 1 revolution. The shaft turns at a certain speed in RPM or Hertz, and we can calculate that by saying 1 divided by the value in Hertz is the number of seconds. So that's the number of seconds that it took to rotate. And if we wrap our time waveform around that, well, what do we see? 1, 2, 3, 4 events per rotation. And because it's sort of this nice smooth pattern, we know that it is exactly 4. If it wasn't exactly 4 events per rotation, then these would all overlap. If I had a lot more time to tell you about circle plots, then I could demonstrate that. In this particular case, we've got, I forget now, but quite a few events per rotation. Let's just call it 31 like our gear before. Nice prime number. So if we expand that out, so this is now a situation like our gear mesh. 1 gear mesh, 2 gear mesh, 3 gear mesh. And if we wrap that around our circle, hey, it even looks a little bit like a gear, doesn't it? Because there's a gear mesh, gear mesh, gear mesh, gear mesh, gear mesh, etc., etc. And because, of course, with one rotation, with a gear, we've got an integer number of events per rotation. Hey, there's an integer number of teeth. Therefore, our circle plot looks good. You know, we've got our time waveform. It's wrapped around the circle plot. And in this beautiful, simple case that I'm showing here, you know, we can see very clearly that the vibration as the gear turned is uniform. Each mesh is the same, but I can see it very clearly. Now, rather than waiting for that to finish, now I'm going to show you a different sample. So here's the same gear mesh frequency, but once per revolution I've got a little spike in the vibration. Let's imagine that there's a damaged tooth or something like that. So here's the same thing we looked at before, but once in the revolution we've got this spike. Now, yes, it's very simple the way I've depicted it, but the point is that when you wrap that around a circle plot, we can see quite clearly what's going on. You know, if we wait long enough, they will just keep overlapping on each other, and the big spike, so here it comes, there's the broken tooth coming down, it will sit right on top of that same spot. So if you look at a real circle plot from a machine with a damaged gear, a damaged tooth, you will see, you know, some normal sort of amplitude vibration around the plot, but in one spot you'll see this big spike. If there were 2 teeth next to each other, you might see, you know, a broader spike here, or even 2 spikes. But let's say there was a damaged tooth, and then there were a few good teeth and another damaged tooth, and you'd see a spike here and a spike there. And with time synchronous averaging, hey, you can even figure out where they are, because you know that this is the start of the tach signal. You can even say, well, okay, you know, 1, 2, 3, 4, 5, 6, 7 teeth around from where the tach reference was is where the damaged tooth is. Now that'll really freak out any of the guys working on the gearbox when you can say, yeah, not only do I know that there's a damaged tooth, I can tell you which one it is. Man, they're going to be impressed. But anyway, I'll just briefly mention that, you know, we use techniques like enveloping, demodulation, peak view, shock pulse, etc. Typically we use that for bearing analysis. The reason is that in the early stages of a bearing fault, we get this impact, but it's a very low amplitude event. You know, if we can visualize the bearings rolling around, there's a little bit of damage on the outer race, the ball rolls across that, so maybe 6.7 times per revolution we get this little spike. In the normal spectrum it's kind of being swamped out because there's all other higher sources of vibration. It's a very short event. It may not be picked up very well in the FFT. There's a lot of issues there. But because we see that as a spike which causes excitation in the higher frequencies, we're exciting higher frequency natural frequencies in the structure or in the sensor itself, we can use a demodulation technique, whether it's peak view or shock pulse or whatever. We're taking advantage of that factor. We're filtering out all that lower frequency, higher amplitude vibration. We go through an enveloping process which allows us to see that not only as a time waveform but as a spectrum. But bearings aren't the only thing inside a machine that can cause that impact, which can excite those natural frequencies. If we have damaged teeth, then the same thing occurs. If we have looseness and we're getting a once per revolution impact, the same thing occurs. If we have broken rotor bars, the same thing can occur. The impact is exciting the high frequency natural frequencies. The natural frequencies that exist in the machine up above, to say 2,000 or 3,000 hertz. We can talk about this in terms of stress waves and shock pulses and so on. The bottom line is we can detect that in high frequency, in the high frequency part of our spectrum, if we use these same techniques that we use for bearing analysis. And you may have seen it already. You might be looking at your peak view spectrum or waveform or your shock pulse or whatever and see 1x vibration and think, whoa, why am I seeing an increase in 1x? Well, it's because there's probably looseness, or it could be one tooth damage in the gearbox. Once per revolution we're getting this stress wave. So we can use those same techniques to detect gear faults as well as bearing faults. And once we have the time waveform, from that enveloping process, we can look at the time waveform. We can look at it as a spectrum. We can even wrap it around a circle as we did just before. So they're very useful techniques. Anyway, this has been a very long presentation. I hope you've hung in there with me. I normally try to keep them a bit shorter. This is a big topic, so I hope you found it useful. A few quick factors. You do have to think about gearboxes very carefully to make sure that where you place your sensors, you're capturing the frequencies of interest, there's a good mechanical transmission path to that point, and that your measurements are being set up correctly. Spectra are useful. Enveloping and the various techniques are useful. Time waveform analysis is very important. Have a look at time synchronous averaging, have a look at circle plots if your software has it. Think about the criticality of the gearbox and how important it is that you get all this right. Think about the failure modes and the PF interval to make sure you're taking your measurements frequently enough. And also think very carefully about oil analysis to make sure it's being lubricated correctly without contamination, and wear particle analysis excuse me, so that you can detect those particulate contaminants but also detect any wear that's going on. So thanks for viewing this presentation or mini training course, however you might want to look at it. As you probably know, we've got lots of other presentations on our website on a range of topics. I'm going to do one on modulation to help explain that, because that's something that sort of comes up quite frequently as a question. Of course, you can click off at this point, but I'll just tell you that we've got lots and lots of training courses and products that explain all of these principles in much greater detail. It is really important that you understand how to take measurements properly, ranging from how you mount the sensor to how you set settings like resolution and Fmax, how you analyze the data, how you determine when phase analysis is important, time waveform analysis, spectrum analysis. But there's a bigger picture story here, and that relates to reliability. It's fantastic to use vibration to detect faults. It's very important you look at your maintenance practices and the way the machines are being operated and the selection process for new components and lubricants and so on, so that we find these faults less frequently. We need to improve the reliability so that we don't have faults to detect. The most important thing is that we increase reliability, so we reduce downtime, we increase the confidence we have in the plant, we increase the safety in the plant, and that's just great for job security. You keep the plant and the business financially secure, and your job is financially secure, and it's a safer work environment. Anyway, we have lots of training that cover all those sorts of topics in iLearn Reliability and our Category 1, 2, 3 and 4 training courses. Anyway, thank you very much for listening to this presentation. Bye.